In this video, we will go over the process of creating complex matrices of different types. A matrix is similar to an array but will have more rows and columns. I would recommend that you go through the first MATLAB course geared towards beginners level for simple matrix creation. Let's start with creating a matrix by combining two matrices together. For example, assume that we are given a matrix A which is equal to 2, 2, 4, 4, and then a matrix B which is equal to 6, 6, 8, 8. Now let's combine these two matrices together to create a matrix C which is equal to A and B. And that will give us a new matrix which has in the first row the first elements of the first row of matrix A and the first elements of the first row of matrix B. And in the second row, we'll have elements of matrix A second row and elements of matrix B second row. Now let's create another matrix D, which will combine again A and B, but A semicolon B. And then now we can see how it puts together the two matrices but column-wise. A powerful tool when creating matrices is using the colon operator. You can create large matrices with it. For example, let's say we are going to create another matrix A that will be equal to 1 colon 10. And if the step is not specified, then by default it's 1. And then the second row will be numbers from 11 to 20, again with a step of 1, and press enter. So we can see the large matrix A with elements in the first row from 1 to 10, and in the second row from 11 to 20. Another way of creating matrices is by manipulating already created ones. Let's start by creating a matrix called angles. And this matrix will contain angles from 0 to 360 with a step of 30. Now let's create another matrix that will be called trig values, the first column of which will contain the angle values of the angles matrix that we created before. So trig underscore values. And this will contain the first column will be the elements of the angles matrix. So this will be equal to angles. And then press enter. And we are going to add another column to this matrix that will contain the calculated sine values of these angles given in degrees by using the sine d function. So again, we are going to call the trig values matrix, but in this case, we're going to use the second column element, and that will be equal to sine d, so using the sine d function of angles. And then the third one will be using the same matrix, but the third column will be now the cosine values of these angles. So the third column will be equal to cosine d using the cos d function of angles. Now let's assume that we want to create a table with matrix trig values and add the headers for the angle, sine, and cosine. So the variable names that we are going to give will be angle, sine, and cosine. To create this table, we are going to use the table function. So I'm going to call this new variable t, which will be equal to table function, and then we are going to use the trig underscore values matrix here, and that will have the first column, then again trig values, and this will contain the second column, and again we're going to call the trig values matrix the third column. And also we are going to add here the variable names. So variable names, which in our case will be the names for each column for angle, sine, and cosine. So we are going to use the curly bracket here, and then the first variable name will be angle, comma, the second one will be sine, and the third one will be cosine. So now we can see that we created a table with the angles from 0 to 360 here, so 0, 30, 60, 90, and so on, the sine values and the cosine values here. MATLAB also offers functions to create complex matrices, such as the block diagonal function. This function is used to create a matrix based on 1 to n matrices and combining them diagonally and filling the rest of the elements with a zero value. For example, let's create another matrix, A1, which will have the values 1, 2, semicolon 1, 2, and then another matrix A2, which will be equal to 3, 4, semicolon 3, 4. We are going to get a new matrix B using the block diagonal function. So BLK and diagonal, and then A1, comma A2. And this will give us a new matrix that, as you can see here, fills with A1 and A2 diagonally, and the rest of the elements will be just zero. So finally, let's see how we can create a sparse matrix for a given matrix. Sparse matrices are a type of matrix in which most of the elements are zero. They are particularly useful in computational applications where memory efficiency and speed are important. In case you have a large matrix that contains a lot of data, where many of them have a value of 0, you can reduce the size of the matrix by using the sparse function. For example, let's create a matrix A, which is a combination of ones, zeros, and random values. So our matrix A will be based on ones, and I'm going to have dimensions 5 by 5. The second one will be zeros, and again, same dimensions 5 by 5. And the other one will be using the random function with the same dimensions. And this will be our A matrix. And as you can see here, this matrix is a combination of ones, zeros, and random values. So if we use the sparse of this matrix A, then we are going to end up with a matrix that will actually have no zeros in it. It will be just combination of the ones and the random values. In the next video, we will take a look at some of the matrix arithmetics. First, let's talk about matrix addition and subtraction. These operations are straightforward and require that the matrices have the same dimensions. Let's use the new live script tool, which is found under the Home tab, that allows you to test your programs without needing to save them and without needing to add them to the MATLAB path. So I'm going to create a new live script here, and we are going to write the code in here for matrix addition and subtraction and display both the original and the new matrices created by the addition and subtraction. So I'm going to copy and paste here two matrices that I have created from before. So I'm just going to press copy paste here, but also I am going to put a comment. And for the comment, as we know from the previous course, we are going to use the percent icon here. And then I'm going to type matrix addition and subtraction. So if I save this and go back to it, then I know what this code is about. Then I'm going to separate into two matrices, C and D. One will be to store the addition of A and B, and the other one will be to store the subtraction of A and B. So I'm going to write a new comment, and this one will be just addition. And I have C, which will be equal to A plus B. And then semicolon to suppress the output. I'm going to put a new comment, subtraction, and variable D, which will be equal to A minus B. Now we are going to use the display or the disk function that will display all matrices, but also we are going to display text. So first I'm going to use the display function to display matrix A, and then display function again, but to display the values of matrix A. And then I'm going to do the same thing for all the other ones. So what I'm going to do here, I am just going to copy and paste this code. So now I have in my code the two original matrices, A and B, the addition, subtraction, and display all the text and the values of each matrix. So once we are here in the live editor, so make sure that you are in the live editor, then you can click run. And then on the right side with the live script, you can see that you can actually show the values. So we have matrix A, matrix B, A plus B, addition and subtraction. Now let's discuss matrix multiplication. Unlike addition and subtraction, matrix multiplication is not element-wise and requires the number of columns in the first matrix to match the number of rows in the second matrix. Matrix multiplication involves taking the dot product of rows from the first matrix and columns from the second matrix. So let's create now a new script in a new live tab, which you can access by clicking on the plus sign next to the previous one. So again, I'm going to start with two matrices that I'm going to copy and paste because I've already written these matrices before, and then paste them here, but also because I want to know what this is about, I am going to put a comment here and say matrix multiplication. And then the next one will be adding a new matrix, which will be containing the multiplication between A and B. So I'm going to call this matrix E, and that will be equal to A multiplied by B. And then same way we did the first one, we are going to display each of these matrices. So I'm going to copy paste the code and paste it here, and then display matrix E values. And then I'm going to run this code one more time. So we can see the original matrix 1, 2, 3, 4, 5, 6, matrix B 7, 8, 9, 10, 11, 12. And you can see that matrix A is a 2 by 3 matrix and matrix B is a 3 by 2 matrix. So you can see how they match the columns from the first matrix, match the rows from the second matrix. And then we have the multiplication between A and B here, shown here. Now let's take a look at element-wise operations. For element-wise operations, multiplication and division, the matrices must have the same dimensions, and we use the dot operator, so dot multiply and dot divide in MATLAB. Let's write these commands in the command window this time. So I'm going to leave the new live scripts and reduce the space and have my new code run into the command window. So I'm going to type A, which is my new matrix here. So 1, 2, 3, and then 4, 5, 6. And then suppress the output. And then we have B will be equal to, I like to put some spaces here. So 7, 8, 9, and 10, 11, 12. Suppress the output again. And now let's have F will be equal to A dot multiplied B. So this will give us element-wise production between the two. And as you can see here, we have 1 multiplied by 7 will give us 7. 2 multiplied by 8 will give us 16. 3 multiplied by 9, 27, and so on. So this is the first row and the second row here. And also we can do the same thing with division. So let's have another variable g that will be A dot divide B. And then we'll have numbers that will be 1 divided by 7, 0.1429, 2 divided by 8, 0.25, 3 divided by 9, 0.3333, and so on. So two last operations that we are going to cover here are finding the maximum number of linearly independent column or row vectors in a matrix. For example, let's say we have, again, a matrix A that is equal to 1, 2, and second row 3, 4. And I'm going to create another variable that I'll call A rank, which will be equal to rank. That is a function in MATLAB that actually exactly shows the rank of A. So what is the rank of A? So that's, again, the maximum number of linearly independent column or row vectors in a matrix. So I'm going to use the display of A rank, and that should be equal to 2. And it is equal to 2 because the two rows or columns, the elements for each row and column, they are independent from each other. So first row and second row, they are not dependent on each other. But let's say, for example, if I have A, again, let me go back and get A so that I don't have to write it again, like not all of it. And let's assume that we are going to put 2 and 4 in the second one. And now let's go back, and again, using the up arrow, I'm going to get the A rank one more time. And then the last one, using the up arrow again, use display A rank. So now I can see that the rank is 1. Why? Because we can see the relation between the elements in the first row and in the second row. First row is 1, 2, second row is 2, 4. So 2, 4 is dependent on row 1 element. So if you multiply 1 by 2 and 2 by 2, you get row 2. So this is how we define the rank of a matrix. Now, also, we're going to take a look at the trace of a square matrix, which calculates the sum of its diagonal elements. For example, let's get the same matrix again. So I'm going to pick the first one, which is the here, and then go down. And let's assume we create another variable that we will call A trace, and it will be equal to, using the trace command, A trace of A, and then let's display A trace. So we can see that this is 5, and that will give us, again, this calculates the sum of its diagonal elements. So we have 1 plus 4 will be 5, and 3 plus 2 will be 5 in this case. In the next video, we will go over matrix factorization techniques. In this video, we will go over the process of matrix factorization, which involves breaking down a matrix into simpler, more manageable components. We'll cover a couple of the most common factorizations today, starting with the lower upper decomposition or factorization, which is particularly useful for solving a linear systems of equations. Lower and upper triangular matrices are square matrices that have all elements respectively above and below the diagonal zeros, as you will see in this slide. So let's assume you have a matrix A, which must be a square matrix, and the blue decomposition factors this matrix A into a lower triangular matrix L and an upper triangular matrix U, such that A will be equal to the product of L and U. So let's assume that we have a matrix A here, which is given as 4, 3, 6, 3, so a simple 2 by 2 matrix. And then based on the factorization, this is divided into an upper matrix U, which will have any elements below the diagonal zeros and the elements above it non-zero. And the lower matrix, which will be the matrix that will have any elements above the diagonal zero, the diagonal elements of this matrix will be ones, and then any number depending on the factorization that will be below the diagonal will be just a number but not zero. We are not going to cover the mathematical explanation of this factorization. Now let's talk about QR decomposition. This factorization expresses a matrix A as the product of an orthogonal matrix Q and an upper triangular matrix R. An orthogonal matrix is one that its inverse is equal to its transpose. Multiplying Q by its transpose QT will give you the identity matrix. There are different techniques used to find the Q and R matrices. One of the most common used ones is Gram-Schmidt. Now let's go back to MATLAB. Let's start by creating a new live script. So I'm going to click again on a new live script. And let me open this one so we'll have space to see. We will add a comment first, and we will do the Lu decomposition example or factorization. And then let's create a matrix A, which I'm going to copy and paste here and suppress the output. And then we are going to use the Lu function, which will decompose matrix A into a lower and upper triangular matrices. So we'll have L, U will be equal to using the Lu function of A. And then let's display all matrices. So again, I'm going to use the display function. So I'll have display A. And then I'm going to write display. So the text for the lower triangular matrix L. And then display L, so the value of matrix L. And then we'd do the same thing for displaying the upper triangular matrix U. And then display U. Now let's run this program. So we can see that we have the original matrix A, and as you can see here, I didn't actually write a text for this one. But it's good to do that as a practice so that you know which matrix is which one. And then we have the lower triangular matrix L and an upper triangular matrix U. So the lower will be, in this case, as you see here, has all the diagonal elements are 1. And then for the triangular upper matrix, you can see that some of these elements, because I put all the elements of A as 5, 5, 5, 5. So then when you multiply L by U, you'll get this matrix, the original matrix A. So now let's create a new code that will use the QR decomposition method. So we are going to start with the matrix. We can either start a new live script or we can just use this one and replace this one. So instead of having A as 555, I'm going to rewrite the A matrix here. So this will be now 1, 1, and 1, -1, 1, 0. And then instead of using the loop function, we are going to use the QR function. So now I'll have the Q and R matrices. So the orthogonal Q matrix and the upper triangular matrix. And now the function will be QR. And then we are going to display. So in this case, I'm going to add display, so text matrix A, so that we have all matrices here. And then display, the first one will be the orthogonal matrix Q and the upper triangular matrix R. And in this case, now we'll have display Q and display R. And then we run the code again. So now we can see here, matrix A is my original matrix, 1, 1, 1 minus 1, and 1, 0. And then the lower orthogonal matrix Q and the upper triangular matrix R. So these two matrices that I have here, when you multiply them, you'll get matrix A, and also we have the orthogonal matrix, which is a square matrix that, if multiplied by its transverse matrix, will give you the identity matrix. These are two examples of matrix decomposition methods used in MATLAB. You can explore MATLAB documentation for other techniques. In the next video, we will look at eigenvalues and eigenvectors calculations in MATLAB. What are eigenvalues and eigenvectors? They are special scalars and special vectors associated with a matrix. They are used in data analysis to reduce noise, in linear differential equations, and in engineering and science. The key concept is that when a square matrix A acts on an eigenvector V, it simply scales the vector by the eigenvalue lambda. Equation that we use is A multiplied by V, which is the eigenvector, is equal to lambda multiplied by V, where lambda is the eigenvalue. Now, this equation can be modified to be written as A multiplied by V minus lambda V equals 0. And we can factorize V where A minus lambda I is equal to 0, where I is the identity matrix. Now let's see how we can find the eigenvalues. First, we need to calculate the determinant of A minus lambda I equals 0. So when the determinant is equal to 0, then you can find lambda values. So the matrix A, the determinant of matrix A is given as A11 for first row, first column, A12, A21, A22, minus lambda multiplied by the determinant of the identity matrix, which has all the diagonal values 1 and all the other elements as 0, and that will be equal to 0. Let's take an example. So let's assume that we have a matrix A, which is 4, 1, 2, 3, and then we are going to calculate the determinant of A minus lambda I in order for us to find the eigenvalue lambda. So we'll have 4, 1, 2, 3 minus lambda multiplied by 1, 0, 0, 1 for the identity matrix, and that's equal to 0. So further, we are going to multiply lambda now. So we take lambda inside the 1, 0, 0, 1 matrix, and then we have lambda 0, 0, lambda. So now we can modify this further, and we will have just one determinant, which will be 4 minus lambda 1 and 2, 3 minus lambda, and that's equal to 0. By multiplying the opposite diagonal elements and subtracting them, so we'll have 4 minus lambda multiplied by 3 minus lambda minus 2 multiplied by 1, that's equal to 0, so that we can write this second order equation with lambda as the only unknown. That's lambda squared minus 7 lambda plus 10 equals 0. And from this one, we can calculate the values of lambda, which in this case are 5 and 2. So once we have these two values, then we can use these eigenvalues to calculate the eigenvectors. So for lambda equal to 5 and lambda equal to 2, we actually find that V1 is equal to V2, where V1 and V2 are the eigenvectors. So we have V1 and V2, any numbers that can give us a value of 0 if multiplied by the determinant of 4 minus lambda 1, 2, 3 minus lambda. And then for lambda equal to 2, we identify V1 equal to minus 0.5 multiplied by V2. Now let's go back to MATLAB. Let's start with an example. So we will assume that we have the same square matrix that I went over on the PowerPoint slides, and that matrix is A equals to 4, 1, 2, 3. By using the IG function, we can find the eigenvalues and the eigenvectors of this matrix. So let's start by creating a new live script to find these values. With the new live script, which again we can find under the Home tab, we are going to run a new code. So I'm going to start with a comment. Define a square matrix A, and our matrix A will be equal to 4, 1, 2, 3, and then I'm going to suppress the output here and writing another comment, which is computing the eigenvalues and eigenvectors. For this matrix. So we are going to use the eigenvectors, comma, eigenvalues, and that will be equal to the function eigen of A, which is the function that will allow us to do the calculation of the eigenvectors and eigenvalues. And then let's display first text of matrix A, so the original matrix, and display A. And then we are going to display the text for the eigenvectors. And then display eigenvectors. And similarly, we are going to, or I'm just going to copy and just change. And then display, copy and paste, just display values here. And then we can run. As you can see here, actually I ran into an error that shows that I wrote this wrong here. So as you can see, it's eigenvalues. So I have a V and D extra here. So I'll try to set fix here and then run the program one more time. And so now we can see the eigenvectors values and the eigenvalues. So for the matrix A, which also is the same one that I showed you in the example, We have the eigenvectors 0.7 and 0.7. That's for lambda 5, which is the first eigenvalue, and those are the same. So v1 equals to v2. And for the second one, where lambda is equal to 2, we have the v1 minus equal to minus 0.5 v2. And as you can see, the first one is half of v2 here, and that's for lambda equal to 2. While we are in the live editor, we can use the control tab, and I can add here a slider. So for example, if I am on the value of one of the values of matrix A and I go under the control tab, I can go and use the slider. So once I use the slider instead of the value, then I can change this value to different values. So if this one was 4, here I can see the matrix A eigenvectors and eigenvalues. And then if I change, then I can see different values for eigenvalues and eigenvectors here. So this way I can control any of the elements of this matrix. In the next video, we are going to dive into practical examples of using eigenvalues and eigenvectors.